Congratulations, class. You made it through the first 4 weeks of statistics. And the last week is kind of a standalone unit almost. So it uses a little bit of what you've learned so far, but you can pretty much do this unit without having completed units 1 through 4. So this week we'll learn about bivariate data and regression line. Bivariate data consists of ordered pairs, where one part is considered the independent variable and the other part is the dependent variable. You'll learn how to find the correlation or the relationship between the pairs of data, and you'll also determine the strength of the correlation. In addition, you'll learn how to calculate the regression line or the line of best fit for your data. So this week's objectives are identifying bivariate data, calculating the linear regression, calculating the correlation coefficient, and then stating the strength and direction of correlation. So this week is from chapter 9 of your textbook, which is called Correlation and Regression. And section 9.1 is about correlation. 9.2, we learn how to calculate the linear regression. And 9.3 are measures of regression and prediction intervals. So that's what we'll be covering in chapter 9. So let's go ahead and get started. And then the other thing that happens this week, in addition to chapter 9, which is your Unit 5 homework, we will also have the Unit 5 final exam. I'm sorry, not the Unit 5. The course final exam also takes place this week, and the final exam covers everything that you've learned in the course. And then I was just checking, I believe there's no Unit 5 quiz. Yes, there's no Unit 5 quiz. So in week 5, we do the Unit 5 assignment in my stat lab, and then there is a practice final exam and the final exam. All right, so let's get started on correlation. So as I mentioned, section 9.1 covers correlation. And what is correlation? It's a relationship between two variables. So first of all, the data needs to be represented by ordered pairs X and Y, and we can graph these, okay? So X is the independent or explanatory variable, and Y is the dependent or response variable. And we can use a scatter plot to determine whether a linear or a straight line correlation exists between two variables. So in this class, we only look at straight line correlations, okay, linear correlations. So here's an example. So our data consists of the ordered pairs 1, -4, 2, -2, 3, -1, 4, 0, and 5, 2. So when we graph these, here's 1, -4, 2, -2, 3, -1, 4, 0, and 5, 2. So remember, this is our x-axis, this is our y-axis, and this is how we graph an ordered pair in the coordinate plane. And then we have different types of correlation. So first of all, negative linear correlation occurs when the slope of the line is negative. So this happens when as x increases, y tends to decrease. That will give us negative linear correlation. And then if as x increases, y also increases, that'll give us positive linear correlation. So if there's negative linear correlation and we draw a line through the data, our line will have a negative slope. So this kind of looks like it's that the slope is about -1, and this kind of looks like the slope is about +1, but it doesn't matter. The line could be more flat. If it has a negative, if there's a linear correlation and the line has a negative slope, meaning as x increases, y decreases, then it has negative linear correlation. Okay, so even though they drew it like this, that doesn't really matter. Okay, if y increases as x increases, even if the slope were more flat or more steep, if it has a positive slope, then we would have positive linear correlation. And when you see here that it just looks like the data is kind of all over the place and I can't really see a line, it could go in any direction, right? This one has no correlation. And then this last one shows us a nonlinear correlation. We can see clearly the data is correlated, but it's in a curve. And the way that we would do this, if we want to do it with the materials we learned from this class, is we would just transpose or transform this data. So we would do a transformation on the data set. This looks like a negative x squared, but usually we do a log transformation so that we can get a linear. And then once we have the new data, that we graph that and it'll look like it's correlated or like it has linear correlation. Okay, so the first thing that we learn about is the correlation coefficients. We already talked about the types of correlation. So we actually measure this using a correlation coefficient, which is a measure of the strength and direction of a linear relationship between two variables. So again, this only works for linear relationships. So when we look at this last one, which is nonlinear, we would find that our R would show that there's no linear relationship. So R represents the sample correlation coefficient. So this is just the representation. We use the symbol R. In statistics, R always represents the sample correlation coefficient. And this is the formula for R, and I know it looks kind of crazy, but I'm going to show you how to do this in Excel without using this long, drawn-out formula. But N is the number of ordered pairs that we have. And basically what we would do is we would put a column in Excel, we put in a column of our X values, a column of our Y values, and then we would create a new column where we multiply those together, and then we would sum that. Okay, we would multiply that by N and subtract off the sum of X times the sum of Y. And then we would create another column, which is our X squared values, and we'd sum that. And then we would use our sum of our X values and square that. So this is, we square the X's and then we sum those squared values. And this means we sum all the X's and then we square that. Same thing with the Y's. So this can be done pretty easily in Excel, calculating this. It's not hard to set it up to use this formula. But again, there's a function in Excel called correlation. So we're going to use the correlation function to calculate R. And then the population correlation coefficient, whenever we have anything representing the population, remember we always use Greek letters. So this is the Greek letter rho. So I know it looks kind of like a P, but it's pronounced rho. And this is a Greek letter, okay? And rho always represents the population correlation coefficient. So our values that our correlation coefficient can take are between -1 and 1. So if R is -1 exactly, that means there's perfect negative correlation. In other words, our ordered pairs lie exactly on a line, and that line has a negative slope. If R is close to 0, then we won't see any linear correlation. And if R equals 1, then again, perfect positive linear correlation or perfect positive correlation. And all our values will lie exactly on a line with a positive slope. So here it's showing us kind of what it looks like in real life. So here R equals -0.91. So we can see a line here. And this is strong negative correlation. Here, R equals 0.88. So we can see that this looks linear. And so this has strong positive correlation. Here, R is 0.42. So we can see it doesn't have to be close to 0 for us to start to see that it's hard to see a line. Hard to see a line here, right? You can tell that there is a positive correlation, that Y tends to increase as X increases, but it's not very linear. So this is weak positive correlation. And then here, R is almost 0, and this is nonlinear correlation. So again, to calculate the correlation coefficient, we would find the sum of the X values, find the sum of the Y values. We would create a new column in Excel, which is X times Y, and we would sum those values. We would create another column that is X squared. We would sum those. We would create another one that's Y squared and sum those. And then we would use this formula. Okay, and then we can use a table to test a population correlation coefficient rho. So once the sample correlation coefficient R has been calculated, we want to determine whether there's enough evidence to decide that the population correlation coefficient rho is significant at a specified level of significance. And to do this, we use table 11 in Appendix B in your textbook. And if the absolute value of R, this is the one we calculate from the sample, is greater than that critical value, then there is enough evidence to decide that the correlation coefficient rho is significant. All right, so this is what the table looks like. I don't believe we even do this in the homework. We'll see when we get there. But if you did need to look it up, this is what the table looks like. So using a table to test a population correlation coefficient, it says determine whether rho is significant for 5 pairs of data n. So it's this is how the table looks. It gives us an alpha level, either 0.05 or 0.01. And then it's what value that you need to see significance is based on your sample size. So if the sample size is 5 at n equals 5 and level of significance 0.01, then we need an R of at least 0.959. The absolute value has to be at least 0.959. So anything positive greater than 0.959, so if it's 9.96 or above, that would be significant, or if it's below negative 0.959, right, then it would be significant. Otherwise, there's not evidence to conclude the correlation is significant. So in order to test whether it's significant, we're going to determine the number of pairs of data in the sample. So we're going to figure out what n is, specify the level of significance, alpha, and then use table 11 to determine whether or not significant. And again, if R is greater than that critical value, the absolute value of R, sorry, is greater than that critical value, then the correlation is significant. Otherwise, there is not evidence to support that the correlation is significant. We can also do hypothesis testing of a population correlation coefficient. So a hypothesis test can be used to determine whether the sample correlation coefficient provides enough evidence to conclude that the population coefficient is significant at a specified level. And that hypothesis test can be one or two-tailed. And it looks like this. So this looks like what we did in chapter 7. So a left-tailed test has an alternative hypothesis that rho is less than 0, which gives us significant negative correlation. A right-tailed test has rho greater than 0, which gives us significant positive correlation. Otherwise, if we do not reject the null hypothesis, then there's no significant correlation. And a two-tailed test, again, is the alternative is that rho is not 0. Okay, we use a t-test for the correlation coefficient, and that can be used to test whether the correlation between two variables is significant. The test statistic for our t-test is R, and the standardized test statistic is R over sigma. This is the standard deviation of R. So it's R over the square root of 1 minus R squared divided by n minus 2, and it follows a t distribution with n minus 2 degrees of freedom. And for this textbook, they only do two-tailed tests. So to do the t-test, we're going to state our null and alternative hypothesis. We only do two-tailed tests in this course. So that means we're using this one, the two-tailed test. So our null hypothesis is that rho is 0, and our alternative hypothesis is that rho is not 0. Okay, so we're going to state those. They're always going to be the same thing. specify the level of significance. The degrees of freedom are n-2, and then we use our T table in Appendix B, or we can use T.dist in Excel, and we're going to use the t-test to test for the significance of rho. The standardized test statistic is r divided by the square root of 1 minus r squared over n-2. And then if t is in the rejection, this t that we calculate is in the rejection region from the table, then we reject h naught, otherwise we fail to reject. Okay, and then we interpret the decision in the context of the original claim. Correlation and causation. This is a really important topic in statistics, and it's important because usually the reason we're doing correlation is to say something about causation, but two variables can be strongly correlated, and that in itself does not imply a cause and effect relationship between the variables. So a lot of things are correlated that actually aren't related at all. So some things are correlated for other reasons. For example, a study was done and they found that ice cream sales are associated with higher crime rates. Okay, so the fact that people are buying ice cream does not make crime more likely. It's not ice cream that's the problem. If we closed all the ice cream stores, it would not decrease the amount of crime. The reason that happens is that more crime occurs in the summertime and ice cream sales go up in the summertime. So the summertime makes ice cream sales higher. The summertime makes crime higher. And so it looks like there is a correlation between ice cream sales and crime. So when you look at the correlation, you'll find a positive correlation, probably even significant, but the underlying cause is the hot weather. All right, and it's the cause of both of those things. So a lot of times that'll happen, that there's a third thing that they have in common, and then sometimes it's just completely random. All right, so we always want to ask the question, whenever we see significant correlation between two variables, is there a cause and effect relationship between the variables? Does X cause Y? Is there a reverse cause and effect relationship between the variables? Maybe Y actually causes X, okay, because it doesn't matter whether X causes Y or Y causes X. When you see significant linear correlation, it doesn't tell us which variable is the independent variable and which variable is the dependent variable, so that could be arbitrary. And then is it possible the relationship between the variables is caused by a third variable or even a combination of several other variables? Or is it just a coincidence? All right, so that is the end of section 9.1. So now we can do the homework from section 9.1. So we are now ready to do the homework. Pop this back out. So we are now ready to do our homework. Numbers. Sorry, I was looking to see what they were. So we can do homework problems 1 through 6. So these first ones, I'm going to skip ahead until we get to a calculation because you can answer these. Which is a stronger correlation? So you guys can do these. And remember, there's also a question help available. So if you're not sure, you can go ahead and look it up. All right. And then here we get to some graphs. You guys can also do this. You're going to match the graph to the right, to the correct description. All right, so here is the first time that we have some data. So we're going to look at this one. So we're going to start with here number 6, and this is the last problem you'll be doing from, this is the last one from 9.1. So the table shows the height in inches of 8 girls and their scores on an IQ test. And then you're going to complete parts A through D below. So let's click here to view the data table. So here's our data. So first, let's go open up our Excel, and I am going to add a, I'm going to move this to the end. So I'm just adding a new sheet, and this is chapter 9. Okay, and then, so this is number 9.1. This one is number 6. Oops. Okay, so here is my data. I'm going to copy this, copy to a clipboard, Control C. Okay, and then I'm going to go ahead and paste this into Excel. So this is my data that's given. X is the height, Y is the IQ score. Okay, and then here we can get our critical value, which we need for part of this. So first it says display the data in a scatter plot, choose the correct graph. So instead of just trying to look, let's go ahead and graph it. All right, so to graph this, I'm just going to mark my data. If I include this, it'll include these as headers. And then I am going to go insert. And by the way, I created a whole video for you guys on how to create graphs in Excel. So we're going to go insert, and then we're going to pick this, and we want a scatter plot. So I'm going to pick this one. Okay, and so it tells me, so here's my X values, which are the height. And the height should range from 55, or as you can see here, 55 to 65. And my IQ scores range from 96 to 126. So make sure that you graphed it in the correct order. So that's the first thing. And then you'll notice here that my graph does not look like their graph. And that's because of the range. So their goes 52 to 68. So that's about what I have at the bottom here. That's fine. But the y-axis goes from 90 to 130. So I'm just going to show you how to change that. So the way we change that is we click here. And then when we double click on this, this will pop out. And I'm just going to change this minimum to 90. Okay. And I can make it go 90 to 130 to match what they did. I think that'll fix it. Now it goes from 90 to 130. I can also change the x-axis to go from 52 to 68. I don't need to because I can see it. All right. And then the other thing that makes mine a little different from theirs is more square. So let me just pull my sides in a little bit. Oh, I should make this bigger so you guys can see it. Okay, so now mine looks more, Control Z will fix that. Now mine looks more like theirs, right? So now I should be able to look and see which graph matches. And it looks to me like it's this first one. And we can also see what's wrong. So this one, they switched and they have the IQ scores here and the height here. So this one's wrong. Okay, and the same thing with this one. And then this is not what my data looks like. So it's A. All right, and then it says calculate the sample correlation coefficient. So I wanted to show you how to do this in Excel. And there are two ways to calculate this in Excel. So we can go equals, and there's something called Correl. Correl, this returns the correlation coefficient between two data sets. So I'm going to go ahead and hit tab to grab this. And then it says array 1. So I'm just going to highlight the X values, comma, array 2. I'm just going to highlight the Y values. Okay, and this returns my correlation coefficient. And the correlation is 0.00. It wants it to 3 decimal places, 0.004. Okay, so we could create the other column. We could sum the x's, sum the y's, create a column that's the x squareds, create a column that's the y squareds, create a column that's x times y, and sum all of those and use the formula, but you don't need to use the formula. So this is R. Let me move this over. I'm going to go Control X. I'm just going to put this here, Control V, and this is R. Okay, and again, the way that I found R, I thought I made this bigger. So R is just, we use the formula CORL equals CORL, and then your X values, comma, your Y values. Okay, and then describe the type of correlation, if any. So this is really close to 0. So for this one, there is no correlation. If you get a different value, then you'll want to pick the right answer that matches your data. And then interpret the correlation. So I don't have a correlation. So there does not appear to be any relationship between heights and IQ scores, which is what I would expect. Oh, whoops. That's not true. I clicked this. There's no linear correlation. I didn't read them all. Always read them all. Based on the correlation, there does not appear to be a linear relationship. Okay, because that's all we're checking, linear relationship, not no relationship. Okay, and now we're going to use the data of critical values to make a conclusion. So our alpha is 0.01. And our N was 1, 2, 3, 4, 5, 6, 7, 8. It said here. So our N was 8. So our alpha is 0.01. Okay, so N, I'm just going to put this down. N is 8. And then my degrees of freedom is N minus 2. So this is equals N minus 2. Okay, so my degrees of freedom are 6. So my alpha level is 0.01. So then here's the table. So our alpha is 0.01. Our degrees of freedom is 6. So the critical value is 0.917. So the critical value is 0.917. Therefore, there is not, okay, because our R has to be, our absolute value of R has to be greater than this for there to be evidence at the 1% level to conclude there is significant. So there is not evidence to conclude that there is significant linear correlation between high school girls' heights and their IQ scores. Did I miss something? Oh, I should have paid more attention. Down to not evidence to conclude that okay, let me check again and see what it said I did wrong. At least one of your answers is incorrect. Okay, maybe I looked up the wrong one. Let me go back. My alpha level was 0.01. And my degrees of freedom is 6. My alpha level is 0.01 and my degrees of freedom is 6, 0.917. Make sure I wrote it right then. This is the problem when I'm taping and you guys aren't in class to tell me what happened. Okay. Find the critical reason, make a decision. If T is in the rejection region, okay, and the rejection fail to reject. We're not in the rejection region. So we fail to reject H naught. Interpret the decision in the context of the original claim. Still don't see what I did wrong. Let me see. The critical value is this. Therefore, so we failed to reject. Whenever we fail to reject, there is not sufficient evidence at the 1% level of significance to conclude that okay, let me try this. Oh, it said I picked the wrong value. Was I using 0.01 and it was 0.1? Still not seeing what I was doing wrong. Alpha is 0.01. Oh, this is N. My bad. We look up N, not degrees of freedom. Okay, so let me take this out. We don't need the degrees of freedom for the table. Thought we needed the degrees of freedom. You guys probably would have noticed I was doing that. So that the value is 834. And then this was supposed to be, there is not sufficient evidence of a significant linear correlation. Okay, I had that second part right. I thought I did. Sorry about that. Okay, so that's how we look it up. So we look up N, right? So you guys can work on numbers 1 through 6 in section 9.2.